Hello, everyone. Welcome to the class. Today, we are going to talk about the machine organization, especially the machine structure, how your machine execute the code you wrote. When you write the C code, when you write the Java bytecode, when you write like a different code, after you do a compilation, you compile the code to executable file, how your machine actually run this executable file. So let's look at the machine first. So right now, this is the process. We covered this before. For this process, your source code is here, and we have a compiler here. Try to compile it to a assembly code, and the assembly code will use assembler to interpret the assembly code. At the end, you will get this final executable binary, final executable files, the binary files. Then actually your machine is trying to run in these files. But how it's actually do it? This is the idea. So we will send these files, send this file. We load the content of this file to your memory, and this memory will work with this CPU. So you actually use CPU to run this code. But of course, before you run the code, these like binary files, this executable file should be loaded to your memory. Then your CPU can like kind of like run the instructions on these files. Okay, and then the CPU is so complicated. There's a lot of details in the CPU. We will talk about the details in the next videos. But just imagine that uh, in your car, you also have like a lot of different small pieces of machine. You have an engine, you have like a hybrid, like an exhauster. You have so many different like component in a car, right? The same in your CPU. Even the chip is so small, it still contain a lot of information. And we call this architecture. Architecture is kind of very important part. And if you are interested, take an architecture course to understand this more. Okay. So actually, this is the first machine. This is the picture of our first machine, and of course, the man in these pictures, uh, who is the father of modern machines. So you can get the sense. Actually, like 30 years ago, 40 years ago, you can see the machine is so big. It's a computer, you know, the computer is so big and the memory is so small. So actually, this is the architecture of your CPU, architecture of your computer. Okay, so this is the old pictures from like these men. So if we know what's a machine, let's look at let's two different category of the machine. One is called fixed machine. One is called general purpose machine. What's a fixed machine? What's a general purpose machine? Imagine that your calculator. You have a calculator. The calculator, the only function your calculator can do is calculate the mass you try to like give it, the equation you try to give it. So the function of this machine, the calculator, this small machine, is fixed. So you already decide, you already like build everything you need, and there's no software, there's no operating systems, there's just one or couple functions there, and you use these functions. When you use this machine, you use these functions. If you want to change the function, you need to do a lot of like redesign or rewriting. Maybe you need to change the circular like compare circular connection inside the machine. So because this is a fixed machine, so this is an old machine. The general purpose machine is like your computer. So this machine is designed for multiple purpose. Even if you give the correct instruction, then this machine will run these instructions to create the different functions. Just for example, in your computer, you can install different software, right? And different software can do different stuff. So as long as you follow the guideline, write the code can be runnable, and it can create like a multiple like a impos uh incountable possibility. So it can create a lot of different functions. So for you to use. And this is what we call general purpose machine. The general purpose machine need a memory, because if you don't have a memory, how you actually uh reload, like how to load your command. You imagine that your code is like your command. You command this computer to do something. You order this computer to do something. You need to have a space to store this order, and this order we call instructions. You need the space to store these instructions. Then your machine can read these instructions from memory and execute the instruction. So the program stored in memory, and this machine can be reprogrammed. You can kind of provide different program, different code to make the machine do different stuff. This is called general purpose machine. Okay, so this is the idea of your files. You have a C source code, and when we do a GCC, you got assembly or SQL file. Here we show you assembly. Why? Because I want to let you check this is something we are interested in. Why? Because assembly is human readable, but each line of this code can be translated a line of machine code. And this machine code, human, is not readable by human. So actually, you can see each line of this code will change to one line of the machine code. So the assembly is the code most close to your SQL file, but still readable by human. So this is why we use the assembly here. And the following lecture, we want to talk about how your machine actually read your code. And each this assembly code will be translated to one line of machine code. And actually this machine code is runnable by your CPU. So actually the machine code here, like your file here, they are instructions. They are instructions for your machine. Okay. So because the general purpose machine, you try to load this program to memory, and you know what the program look like. The program is actual file, which is this machine code, and we cannot read the machine code because machine code is so ugly. There's no any any vocabulary like English word. There's nothing we can read. Just a lot of numbers there. So in this case, we use assembly, which is human readable, and each line of assembly can match to each line of machine code. This is much easier for us to understand it. So if we want to understand the instructions of your machine, then we can start to read the assembly code to understand what's the instruction you try to give your machine. Now let's take a look at the details of this assembly. Take a look. Okay, so as we say, you have assembly code right now. So each line of assembly can be translated to each line of machine code. So this machine code we call instructions. So what the instruction means? Instruction means your order, your command, what you should do. So for example, you have a recipe. This recipe tell you each step to make to make your dish, right? So you need to add this, for example, 1 and 1/4 flour. You need to add a third quarter cup of your cornmeal. So something like that. You need to follow step by step to create your meal. Of course, there's other instructions. So what's the instruction? Instruction is like a step. Which how many steps you can follow the step. You have a couple steps to follow, and after you follow all steps, you finish the function. You finish the execution. So this is we call instructions. Okay, so instruction actually tell the machine what you should do. You should follow my order. Okay, instruction is the order. So this is the assembly code. Of course, the machine code is not like this. However, each line of assembly code can be converted to machine code. And if you read the assembly code, you probably can get the idea what the assembly code means. For example, the move. Move means you want to copy the memory, copy some data in one memory to another one. Very similar to the languages, right? If you have an integer x equal to y, you copy the value of y and store it to the x, the memory for x, right? So it's the same. Move A and B, try to move a data, not move, actually copy the data from somewhere to another place. So move A, B, move C, B, this kind of stuff. Push and pop is very similar to the stack part. You push the data, you copy the data to some place on your system stack. Okay. Then of course there's some arithmetic operations. You can do the sub unit, you can do the add, you can do the multiplication. So you can have something different like a shift. You can have couple different operators. Actually, they are implemented in your machine. So your machine know what the add means, what the sub means. If they read it in the format of your machine code. And of course, there's some comparison because, for example, your branch, if you have a if statement, you try to compare two variable A and B, equal, this kind of stuff. In this case, we also have some comparison, and this comparison has, because you want to implement a branch, so we have a jump, this kind of like a idea. If it's equal, we jump to like a line 30 or line L1. In this case, we have label. So this is part of instructions. We will talk about the details in other videos, okay? But you got the idea. Each instructions is like this. So even though they are in a different format, they are in the machine level format, but the idea of each instruction is similar. It can compare, it can do the move, it can do the arithmetic operations. They are implemented in your CPU. Okay. So after you do this whole bunch of instructions, your CPU will update the memory's data and use the data in the memory. Of course, what's the data in memory? The data in memory, we will talk about the memory hierarchy in the futures. There's a cache, there's a memory, there's a hard disk, there's a couple different layers of the memory. So this is details for future lectures. And assembly is human readable, but each line of assembly can be converted to a machine code. So machine code, what we say machine code is about the instruction set architecture. So that's a one term called instruction set architecture. It's a predefined. So when you make a CPU, when you make your CPU, you already give the fixed number of this instruction set. So different CPU, different core, different kernel, they have different a different kind of instruction set. So if you use the CPU for Intel's CPU or you try to use the ARM CPU, then you will need to learn different instruction set, unfortunately. So different machine has a different instruction set, but no matter which instruction set, each line of instruction set can be interpreted as an assembly. And the assembly concept will be similar, not the same, but will be similar in different machine. It still supports the arithmetic operation. It supports some like a data copy. It supports some like a branches comparisons. So for all the assembly, but different machine has a different instruction set. Different instruction set match to different assembly code. Okay. So for the instruction set, the bit level encoding for GCC part, because the machine does not understand the character, we call ASCII code. If you remember, a character is ASCII code, right? It's just a whole bunch of number. So actually, the machine code is not readable by human. It's not the same as assembly. The machine code is more like something like this. So you can see, actually the assembly is like sub, CB, this kind of stuff. But if you change to a machine code, the machine code will use a number. Actually, this is number, and it's a hexagonal number here. A3, E, C, E, and C is a hexagonal number because this is each number should be a byte, and each byte is a bits digit. So we use two hexagonal number to represent it. So here we have 3 bytes to represent the order, the command, sub, CB, this kind of concept, okay? So in machine code, we cannot read it, but each line of assembly, we can interpret it to a machine code. So we can read, we can try to understand the instructions by reading the assembly. Okay, so this assembly, each line of assembly will convert to each line of machine code. So actually, when we load this machine, these instructions to your memory, your CPU will read the instruction one by one. The instruction, first instruction, read it, execute it. Read the second one, execute it. Read the third one, execute it, and so on. So it will follow the step. Each instruction is like step. You follow the step to execute the program, okay? So this is how you execute. It's just execute one by one, the instruction one by one, from I1 to IN. Okay, so now we understand there's a couple instructions. How your computer actually run these instructions. Let's take a look at the details inside your CPU. So this is one CPU architecture. There's a lot of different CPU here, and this is just one architectures, okay? So this architecture tell us how to run your instructions. First of all, we have instructions. The instructions will be loaded into here. It will be loaded into here, into your memory, and this memory, this part try to store every information you need. Then your CPU will use different component to run this to execute these instructions. Then let's look at each components. The first component is called control unit. This control unit actually contain a lot of small units there, but the purpose of control unit is interpret the instructions and follow the instructions to do something. For example, if this instruction needs to use the comparison data from previous instruction, then this commander, this control unit will find it and try to understand and try to like tell your machine how to do it. So this control unit part actually is like the first part of your instruction fetch. So when you got the one order, this part will interpret the order. This is the idea. Okay, so instruction registers will store the current instruction. So you will try to load the instruction one by one, right? So you need some place to remember what's the instruction you are trying to do. And instruction counter will try to count how many instructions you already execute. Actually, it will tell your computer, your systems, what's the next line of instructions you want to execute. If you kind of like remember how many you have, then you will know what's the next, right? So the instruction counter is used for store the next instructions. Where's the next instructions? Instruction register store the current instructions. Instruction counter remember where's the next instructions. And usually it will increment automatically. When you load one more, it will try to find the next one. Okay? Then there's a status registers. This part try to state, like try to set some status. For example, I want to compare these two value, and after I compare these two value, where's the result? The status register will store this result. So this result can might help next instructions, because we can have instructions. I'll compare these two. If they are equal, I jump to other place. Otherwise, I don't jump. So the next instruction is jump. You need to let this jump operation, the instruction, know what's the result. So we try to store this result in this part of unit. The decoder read the instructions, then try to decode it. So because you can see the instruction, when we fetch your instructions, it's just couple bytes, a sequence of numbers. How your decoder to interpret these numbers, different machine have a different way to do it, but you definitely need a decoder to understand it. And decoder, after decoder do it, it will generate a signal it will generate signal because right now you already interpret the command. You already know what the command is. So you need to tell each different piece of the machine, you should do your job now. Tell your memory, you should do this. Tell your ALU machine executable unit. You want to tell this whole bunch of stuff something. So you generate the different signal. The signal will send to different piece of your machine, make them wake them up, try to do something. So this is a part of your control unit. The control unit interprets the instructions, try to remember the next instruction, try to based on the current instructions to do something. To it's like a manager, like a commander, command every different piece in your system to do to do something for your new instructions. And the execution unit is very important because every computation, every execution is actually run here. So after your commander decode, interpret the order, and tell this execution unit what you should do, then this execution unit will do everything you need. You want to do a sum, you want to do a product, you want to do subtraction, you want to do a comparison, you want to do a move, everything is here. So execution unit is actually execute the order, the command. Okay? And another part, ALU, is arithmetic logic unit. So inside this execution unit, there's the two part. The first part is the calculation, the arithmetic logic unit. It try to do the math, do the equation. Another part is a register. Register, you can imagine, is a very small memory, but really, really fast memory. It's a very small, tiny, fast memory only support the CPU, this computation. For example, you want to compute the A plus B. So you need to remember A and B in some place, right? So we will get this A and B here. Then your ALU can run this like really fast. So this is part of memory, and we will look at the details for this part in the future videos. And you still have a main memory. So you have a kind of your cache, your like RAM, this memory. This memory can like store a lot of stuff, including your code, instructions, include your data. And every time you try to do this, try to load these instructions, you load it to the control unit. Control unit based on the instruction will tell, okay, I want to read some memory. I want to do some like a computation. It will process it and let your execution unit to do something for this stuff. So this is kind of the architecture of your computer, your CPU. So inside CPU, there are a lot of like different like small piece of unit. Each unit has their job, and when you combine these unit together, they work as a team, and this team work perfect for you and your program. Okay, so this is for today. Today, actually, we introduce how your machine execute the code you wrote. You wrote the code, source code, and use compiler to compile this code to assembly, and in further, it's like a convert to executable files. This executable file actually there's a whole bunch of instructions in the executable file. And your machine read these instructions to your memory, use each like a small piece of the component in the CPU to execute these instructions. The small piece of the CPU, they have a control unit, try to load the data, load the instructions, and like process it, decode it, and let your other part of the CPU to know how to process, how to do the order. Then you have another part, it's the execution unit. This execution unit will execute the instructions, try to do the arithmetic computation or do some other like a command based on the decode result from your control unit. And of course, you have a memory part because the memory part, you need to store the data, you need to store the code, which is instructions here. Then every small component work together to provide you a very good experiments to run your code. This is how our computer actually do in a real world. Okay, so even a small piece, the core is CPU is very small one. There's so many details inside the CPU, inside the chip. So if you want to know more about this, take the architecture course. In the future, you will know how to decide this chip. It's very interesting topic. So see you next time. Today, the machine structure, I hope you like it. And yes, see you next time. Machine organization is awesome.